When we are considering electrons in our orbital diagrams or in our electron configurations, we don't consider them all the same. There is actually some difference from one electron to another. Namely, there are two groups. We have core electrons and we have valence electrons. Now I'm going to explain to you how we tell the difference first, and then I'll explain to you why we care. So the way that we can tell what a valence electron is, a valence electron is any electron that is in the highest occupied principal shell. Now remember, the number at the beginning of the electron configuration sections here, where it's describing an orbital or a subshell, those are the principal quantum numbers. So the 1, 2, 3, or 4 up here in this one, those are the principal shells, the principal quantum number shells. So the electrons that are in the highest occupied principal shell, we call those valence electrons. And it is all of the electrons in that one. It's not just the highest occupied subshell. It is all of them in that highest occupied principal shell. So in the case of silicon, there are 4 valence electrons because we have 2 in the 3s and 2 in the 3p. Both of those are in the third principal shell, which is the highest principal shell that we get to in silicon. And so those are valence electrons. The way to tell what is a core electron is it is everything else. All the rest of the electrons are core electrons. Those are the only two categories. You have your valence electrons, and then everything else is a core electron. So in selenium here, the highest occupied principal shell is 4, and so we have 6 valence electrons in selenium because we have 2 in the 4s and 4 in the 4p. We do not care that 3d is higher in energy than the 4s. We do not care. It does not have bearing on whether it is valence or core. It is still core, even though it is higher up in our electron configuration than the 4s. It is only those electrons in the highest occupied principal shell that are valence electrons. And so it is all the rest of them here. So we have 28 core electrons. Now, the reason that we care about valence electrons is because valence electrons are where the chemistry is happening. Valence electrons are the electrons that are the farthest away from the nucleus. They are physically, as far as like actual physical distance, the farthest away from the nucleus, which means they are the electrons that everything else is interacting with. So because they are the only electrons that something else can interact with, that's where the chemistry is happening. And so those are the electrons that we care about when it comes to chemistry, are those valence electrons. Now the core electrons are still important, like they still have to be there, but they're not actually participating in the chemistry. And again, going back to selenium here, even though we write 3d10 after 4s2, remember this is just because this is a higher energy. It is not actually farther away from the nucleus than the 4s. The 4s is lower in energy than the 3d just because its shape is much simpler. It has different reasons for being lower in energy, but it is actually farther from the nucleus than the 3d. So here we have a list here of all the different elements, at least 1 through 18, and their valence electrons. And one thing I would like to point out here, because this will come in handy later, and I'll bring it up again in later videos when we talk about Lewis structures, but you might notice that the valence electrons exactly match with the old numbering system. So this is the 1A through 8A. The new numbering system, this would be 13, 14, 15, and so on. And this would just be 1 and 2. The number of valence electrons actually exactly matches the 1, 2, 3, 4, 5, 6, 7, 8 here, with the exception of helium. Helium's the weird one. But all the rest of these, the number of valence electrons actually matches the column number. So keep that in mind for later, because it will be very handy when we start doing Lewis structures in a later chapter. And one last thing here I want to cover when it comes to valence electrons and electron configurations. Most of the periodic table is very, very, I guess you could say, orderly. The elements that are in a column together match very well with one another. So for example here, fluorine, chlorine, bromine, and iodine, their electron configurations are all very, very similar. This is why they have similar chemistry, which we're going to talk about at the end of this chapter. They all are some principal number, 2s2 in this case, and 2p5. And you go down to chlorine, it's 3s2, 3p5, and then 4s2, 4p5. But that s2p5 stays consistent. And that is true for most of the elements here. And this is why things in this column have similar chemistries, and things in this column have similar chemistries, because their electron configuration is very similar. The only difference is that the electrons just get farther away from the nucleus as you go down the periodic table. I do want to point out really quickly, though, that the transition metals here, it's not always the case. The transition metals are kind of weird. Sometimes they seem to be following an orderly pattern, like this column here: titanium, zirconium, hafnium, and Rutherfordium, I think that's what that is. But these all have something S2, D3, D2, and the S is always one above the D. But then you have other ones, like this column, where it's different for each one. Every element has a different electron configuration. Those transition metals tend to not follow the rules that we've set forward up to this point. So we're going to ignore those rule breakers for now and just assume that everything is going to follow the rules. By the way, this is one of the easiest ways that professors have to determine if you actually wrote down an electron configuration or if you just cheated and Googled it and put it in. Because if I ask you to write the electron configuration for palladium, for example, I'm expecting you to use the rules that we've talked about up to this point. And if you use those rules, you will not end with 4d10. That will not be your end point. Now, in reality, palladium does actually have 4d10 as the last electron to go into its configuration fills the 4d orbitals. But if you use the rules, you don't get that. And I want you to use the rules. I'm not wanting you to worry about memorizing every exception to the rules. If you were going to be a chemistry major, then maybe you would need to memorize some of those exceptions, or at least understand why there are exceptions to the rules. But we're not doing that. I just want you to use the rules. And so it's very, very common for me to either put in a quiz or a homework or an exam or something, one of these transition metals, and I will get students answering with the answer that they looked up on Google, which, while it is technically correct, the actual element would have that configuration. That's not what you should get if you do what you're supposed to do, which is write the configuration using the rules that we discussed. So don't cheat. Don't look up the answer on Google and just write it down. It is entirely likely you will get the wrong answer in terms of what I am looking for. Because again, I want you to follow our rules. Don't try to find the exception to the rule. Just follow the rules that we've set forward. All right. Real quickly here, I think, yes, this is the last one we're going to do here for this video. We're going to use the periodic table to write the electron configuration for arsenic based on its position. And the way we're going to do this is we are going to notice that on the periodic table here, the periods, so these are the rows, I guess you could say. So we have rows here going left to right, and then columns going up and down. Each of these rows has a period number, 1 through 7, and the period number actually matches the principal quantum number that you start with each of these. So in period 5, rubidium is the first element on that period, and we start with 5s. And so we just continue on from there. This is often sometimes called the noble gas core configuration, where you start after a noble gas and you just essentially say, everything's the same up until this noble gas, and then we pick up from there. So for example, here in this question it says arsenic. So arsenic is this guy. The one below is antimony. I sometimes get arsenic and antimony mixed up with one another. But we have arsenic here, which is element number 33. And so to write its configuration, what we can do, we kind of have a couple different ways we can do it. Like I said, there is one way where you can do the noble gas configuration. I'm not going to worry about showing you how to write that out. We're going to do what is, I think, a slightly simpler way of doing it. But the way that we figure out using the periodic table, if we can cheat with this, because it's already just written there for us, is we would find the element on the table, and we would see which row it's on. So arsenic is on the 4th row, and then we would look at the period or the block that it's in. So each of these blocks here represent one of the subshells. So here we have the S block, here we have the D block, and here we have the P block. And what I mean by having the S, P, and D block is that the last electron to go into the configuration for all the elements in this block goes into that subshell. So every element in the P block, the last electron you put in goes into a P subshell. Same thing here in the D block. The last electron you put into the configuration goes into a D subshell. And so then in here, with the S block, the last electron to goes in an S subshell. And so what makes this kind of convenient for working out what the configuration would be is the S and P subshells will match the period number. The D block is going to be one behind. So it's always, so if you're on the 4th period here, the D electrons that are going in for the 4th period is always going to go into the 3D. It's always one behind whatever the period number is, if you're doing something in here. But since we have arsenic over here, it's on the 4th period. It's in the P block. So we have the 4th period, P block, and it is 1, 2, 3 elements into the P block. This was the first one, second one, third one, which means the last electron to go in was the 3p. And so then at this point, we know where the electron configuration ends. And so we would just fill in the beginning. Just starting there with the 3p, work your way back and fill in everything from that point. So if you don't think that's an easier way of doing it, then don't do it that way. Just do it the original way. But if you don't want to be counting as much, you can, I think anyway, do it easier this way. So just as another example here, if we wanted to write the electron configuration for barium, you would find barium on the periodic table. It's right here. It's on the 6th period in the S block, so we know it's going to be 6s, and it's the second element in, so it's 6s2 is the last electron, and so you just fill into the beginning. Just work your way backwards from there. So you don't need to count electrons in that situation. You just start with 6s, so if you go back here, there's your 6s, and you just work your way backwards, putting in the rest of them. All right. So like I said, that is just an alternative way of writing an electron configuration, or of figuring out what an electron configuration would be. I'm not going to have any questions where I say you have to do it this way, because I mean an electron configuration is going to be correct. As long as you have the correct one, I don't really care what method you use to get it, as long as you didn't just Google it. But if you're comfortable doing it that way, and it's easier for you, then do it that way. So we're going to call it there for this video, and the next one we're going to pick up on our last topic for this chapter, which is periodic trends, and how different properties vary from one side of the periodic table to the other.